All right, so we're now going to move on to, instead of double integrals, triple integrals. And we're going to start by doing triple integrals in rectangular coordinates. And following this, we did talk about polar coordinates. We can also do triple integrals in polar coordinates as well. So this is just the beginning of triple integrals. So we'll start with one setting up an integral for the volume of a solid in the first octant bounded by this plane. This is a plane. I didn't draw the graph yet. Just to remind you, easy way to sketch a plane is to find, if it looks like this, to find your x, y, and z intercepts. If x and y are both 0, z is going to be 6. So I have 0, 0, 6. If x and z are both 0, y is going to be 3. 0, 3, 0. And if y and z are both 0, 3x equals 6 is going to give me x equals 2. So 2, 0, 0. So if I sketch those together, we get what looks like a triangle. If you watch the video on double integrals, we did one very similar to this. The solid itself, this is like the ceiling of the solid where the floor is this little triangle here. And this plane we just drew, this triangular shape, is the ceiling. And we actually did this in double integrals. We did this almost a similar problem, and we already discussed that what you can imagine is filling up this floor with a bunch of vertical columns. So you have a little column like this stretching upward until it hits the ceiling. And you should be, at this point, be able to write a double integral for the volume of this solid by thinking of it in terms of columns. And it's going to be very, very similar. We're going to do this. So if we're using vertical columns emanating from the ground, and we'll talk about how you could change that, all we're going to do now with a double integral, you may remember you had to come up with a formula for the height of your integral right here. But if we do it as a triple integral, it's going to be dz first, because that's going to measure the height of the rectangles. And then just like with double integrals, you can either describe where the bottoms of those columns lie, either in terms of y first and then x, or you could reverse them. So this is giving us the heights of our columns. This is where they all lie. In other words, we use that term, the region of integration. We're going to be integrating all these columns lie in this little triangle. So we will want to describe that as well. But let's start with the columns. Every column we draw in this region is going to stretch from z equals 0, that's your bottom, to z equals the equation of this plane, which means we may need to solve this for z. If you solve this equation for z, you get 6 minus 3x minus 2y. And then we're going to put limits that describe where all these columns lie in terms of y and x. You may want to sketch a separate graph for this region of integration, which is going to lie in the xy plane. And there's a couple of ways to describe this. You can write the equation of this line, because notice this intersects the y-axis at 3. This intersects the x-axis at 2. And so it's a line with a slope of -3/2 and a y-intercept of 3. So you could write the equation as y equals -3/2 x plus 3 is that equation of that line. Also, you can do that if you recall, we did this earlier. This line right here is really this line, which is all of the points on my plane where z is equal to 0. So a sneaky way to find the equation of this line right here is to set z equal to 0 in your original equation, and that gives you 3x plus 2y equals 6, which if you solve that for y, gives you the same thing, -3/2 x plus 3. Okay, so since we're doing dy dx for these limits for y, we would say, okay, for any given x value, what does y vary from? Well, y varies from 0 till I hit my line. -3 halves x plus 3. And that's true as long as x is between 0 and 2. So this would be the volume of my solid in as a triple integral in the orientation of dz, dy, dx. But what we can do, just like with double integrals, we can, or you may be asked to express the volume of a solid with a different order of integration. And so let's practice that. Let's see what that looks like. So here in part B, same exact solid, but we're going to try to describe this solid in the order of dy, dz, dx. And so what that would look like is now we're going to be thinking about for a given z and x value. So z and x would be like in this plane. For a given z and x value, what would y vary from? So what that means is we're thinking about filling this region up with some horizontal columns at certain z and x values. So you could imagine like a little column here stretching outward until it hits the plane. Let's call it a PV column like this. And a whole bunch of columns throughout the region, right, whose lengths, I guess, or heights depend on where they hit the surface. That's supposed to be a column. Okay. So let me get the equation. Remember, the equation of this one was 3x plus 2y plus z is equal to 6. And so in this orientation, we're going to start with y. For a given z and x value, in other words, any one of these points here in the xz plane, what does y stretch from? Well, this is also y equals 0, the xz plane. So that's my lower bound, y equals 0. And they stretch until I hit this plane. But since I have to write it as y, I'm going to solve this equation for y. So 2y equals 6 minus 3x minus z, and then I'll divide by 2. Y is going to go from 0 to this. I'll just write it like that. 6 minus 3x minus z over 2. And then we're going to describe where do all those columns live in terms of z and x, and we have to do z first. So again, it might be helpful to sketch the projection of this solid onto the xz plane. Or another analogy is if you squashed this solid into the xz plane, it would all lie inside that triangle there, which would look, there's z, there's x, goes down like this. This is 6 on the z-axis, 2 on the y-axis, or we can use the trick, same trick as the last one. If I'm looking for the equation of this line, this plane is all of the points, this line right here is all of the points on this plane where y is equal to 0. So if I set y equal to 0 and solve for, it's really 3x plus z is equal to 6, and I can solve it for whichever one I need. It looks like I need z first. So since I'm doing z next, for a given x value, what does z vary from? It varies from z equals 0 to z equals, that's going to be 6 minus 3x. Which is true as long as my x values are between 0 and 2. And so you could probably imagine if you did x first, if you had an orientation where x was coming first, you'd have columns coming out of the paper this way in the yz plane. So you should be able to write an integral really in any of the notations. You should be able to scramble any of these dz, dy, dx, dx, dz, dy, any order. You should be able to set up an integral that would give you the volume. That's a skill that's usually important in 21D. But now if you ask me which orientation is the best, usually for most of the solids, you want to have dz, dy, dx, because dz, dy, dx, as you saw in my first part, that's using vertical columns. And most of the double and triple integrals you set up will almost always be, not almost always, but very commonly will be dz first, and then you could switch the order of dy dx if you need to. But there will be times that you want to use a different orientation if you're given a choice. And the two things you want to think about if you're going to choose an order of integration is the shape of the solid. That might suggest a better order of integration, or what you need to integrate, because so far we're just doing volume. We're just setting up volume with triple integrals. There really is nothing here. You can think of there being a one there to integrate. But very soon we're going to start putting functions there. And then whatever function we put there, you're going to have to start by integrating with respect to the first variable. So you may not like, if there's a function here, you may not want to integrate that with respect to y, for example. And so I'm going to show you an example of each of those ideas. So let's find the volume, or at least set up a triple integral or triple integrals for the volume of the solid in the first octant bounded by these two planes. Once again, I didn't graph it, so we can kind of practice this. So idea of graphing here, this x plus z equals 1 looks like a line that has an x-intercept of 1 and a z-intercept of 1. So you can think of this line right here. I'm going to go use a different color. Now it does keep going, but remember, we're only looking for the part of the solid in the first octant. So it keeps going that way, keeps going this way. And the way, if I was only sketching this, what I would do then is imagine stretching this line out like this in the y direction, because y is missing, and it would be sort of like a tilted plane. And I'm going to hold off on doing that until I see what's going on with this graph. Y plus 2z equals 2 also sort of has the form of a line with a z-intercept if y is 0 of 1, which is where this one is, and a y-intercept of 2. So maybe right here. If I was graphing just this alone, the same thing, I would take this line and stretch it out in the x direction, and that would be a tilted plane as well. Well, if this one's going to get stretched out and this one's going to get stretched out, they're going to intersect each other at a certain point here. So the solid's going to look something like this. This bottom part, I'm going to go ahead and stretch out in the y direction, and I'm going to stretch out the bottom here in the x direction. And perhaps you can see, if I stretch this line out, it's going to intersect this plane, and there's going to be a line of intersection that's going to go from here to here. So let's see if I can color code this. This plane right here, moving that way, that is y plus 2z is equal to 2. And this plane, just tilting upward, that's x plus z equals 1. It sort of looks like a tent. And in fact, to help you see like how we're going to want to approach this, let's think about a top view of this. If I looked at this picture from the top, what I would see is this. This purple part, this line's going to stretch up to 2 and go like this. Everything's going to lie over this rectangle right here, but the purple part's only going to stretch from there, and then the blue part, the other plane's going to be right here. So this is, let's see, this is this one here. That's this one here. I'm just shading it differently, but that's okay. So this is the y plus 2z equals 2. And this is the x plus z equals 1. So the implication of that is, this is like, think of this as a room. The floor is this rectangle, and you have columns coming up and hitting, depending on where the columns start, they're going to hit one plane or the other. And so I kind of have two different ceilings here. So because of that, if we were to use vertical columns, in other words, do dz first, the top view of R, which what we sketched right here, indicates we would need to use two triple integrals because we have two different ceilings. So this suggests maybe not doing dz first. So it would be better to change to either dy or dx first. And I'm going to just arbitrarily choose dx first. We're going to do dx, dz, dy. So what that would look like, here's my same solid. This was my x plus z equals 1 right here. And the other one is right here. If I'm going to do dx first, then I'm going to think for a particular y and z value, a y and z value. So something in this back triangle right here. What would x vary from? Well, that would generate a column that's coming out of the paper until it hits this. So this is like the ceiling of a sort of a sideways room, right, where the columns are coming this way. But notice every column I draw emanating from this back triangle is going to hit this one because they're going to be parallel to this plane. They're going to be parallel to the y plus 2z is equal to 2 plane. So I can get away with only using one triple integral because the bounds for x are going to always be between the back wall and this blue plane here. So that means x is going to stretch from that back wall is all of the places where x is 0 to x equals. So now I need this equation solved for x. That is 1 minus z. And then I want to describe where do all these columns lie in terms of just y and z. So I drew a separate picture for my region of integration in the yz plane. That's just this back triangle right here. So for doing dz dy, what I want to ask myself is for a given y value, some random y value, what does z always stretch from? But in other words, if I put a vertical rectangle in there, well, it would stretch from z equals 0 to this equation. So I'd have to solve that for z. That would be 2 minus y over 2. Which would be true as long as my y values are between 0 and 2. That would be the triple integral that describes that solid. And I could use it to find the volume. So as you can see here, this is what I meant by how do you know which order is best? It kind of depends on the solid. Again, to review, the reason I chose dx first, and I could have probably done it dy first, is because if I had done dz first, I would have had to do true triple integrals because the columns would have hit two different planes as their ceiling. So that's why I changed it. The other thing that can sometimes influence which order of integration is best is what you have to integrate. We haven't yet talked about what it means to have a triple integral with something in there to integrate. We'll get into that soon. But here is a triple integral. We're supposed to integrate this function. And the way the problem stated, we're supposed to do dy, dx, and then dz. And just like with double integrals, if I'm going to integrate with respect to y, then I'm going to be treating x and z as constants. So the 12xz and even this z, they're just pretend they're numbers. So what it boils down to is I'm going to be integrating some kind of a constant times e to the y squared times dy. And okay, maybe you don't know this, but there's plenty of integrals that cannot be integrated with any of the techniques like u substitution or integration by parts. And one of the most famous ones is e to the x squared with respect to x, or in this case, the integral of e to the y squared with respect to y. You can't do it. You can try a u sub, you can try any technique. It's not going to be able to be done. So what that means is I can't really integrate this with respect to y, but if one of the other variables came first, like x or z, then perhaps I could integrate this function. So we have options, right? We can reverse the order of integration, and that would help us find the antiderivative of this function. Now I'm thinking I don't really want to do z first because, again, if you ignore x and y, pretend those are constants, I'm going to be integrating something of the form z times e to the z dz, which is going to require, I left that blank. That's a perfect example for doing integration by parts, you recall from old 21b stuff. So that's not looking too tempting here. So it seems like if we want to avoid that, let's choose x first. Because x, if I hold z and y constant, the 12, all of this is a constant, I can easily integrate x. So we're going to try to switch the orientation here to having x first, and then we'll see what happens with z and y. So to do that, this, with these three limits right here, combined with the orientation and what they go for, this describes a solid. Describes a three-dimensional solid. And we need to look at that solid before we can reverse the order of integration. We need to see what that solid looks like. So, okay, remember those limits. I put them down here. Here's what it looks like. Z in the above integral varied from 0 to 1, and so did x. So for a given z between 0 and 1 and x between 0 and 1, so z somewhere over here, somewhere in this plane, at the zx plane, this is telling me that y, my limits up here, back up here, remember this was y equals 1, y equals x squared. Y goes from x squared to 1. Now the graph of y equals x squared in 3D, here's the graph of y equals x squared in the xy plane, and because z is missing, you extend that in the z direction, so you get sort of a curved surface here. That's my lower bound for y, and my upper bound for y is the plane y equals 1, which would be a horizontal plane here. Now, because z goes between 0 and 1 and x goes between 0 and 1, you can kind of picture that here, that if I were to project this back onto the xz plane, right, that would all fit between this square right here, where z is between 1 and 0 and x is between 1 and 0. And in fact, the way the original integral was described, you can imagine sort of a horizontal, it's hard to draw this, but a horizontal rectangle stretching, or sorry, column, stretching from 1 to the parabola, filling up this region. But we want to do this in terms of x. So we want to have a horizontal column. In terms of x, we want to have our columns coming out of the paper. Maybe pink. Oh, I already have pink there. Let's try purple. I want to have my columns coming this way, coming from that back plane outwards. So if that's the case, what would they're going to emanate from this back wall here, and they're going to start from this back wall, which is the equation x equals 0, and the height of those columns are going to be when they hit this curved surface, y equals x squared, also known as x equals root y. That's what a horizontal column would look like coming out of the paper. But where do these columns lie in terms of y and z? They're all going to fit within this back wall here, this square. In other words, if you squash this whole 3D image into the back YZ plane, they're all going to lie within that square, which has y and z between 0 and 1. So that those horizontal rectangles I was talking about, like imagine a little square here coming out at you, right? That's what I was trying to draw in the previous picture. That's a column coming from this back wall right here. What was this? Okay. So we've got our limits for x. X is going to go from 0 to the square root of y. And it's easy here to see my limits for y and z are both numbers. They're going to go from 0 to 1. And z is going to go from 0 to 1. Let's see why this is going to work out better for us. Again, because I'm integrating with respect to y, that means I get to hold I'm sorry, with respect to x, so right here, this means y and z are constants. So if y and z are constants, the way it works, just like with derivatives, is when you're in, because they're multiplied by x, they just stay there. So I have 12z e to the zy squared, and the antiderivative of x is x squared over 2. And I'm going to plug in from x equals root y to x equals 0, integrate my result with respect to y and z. If I put in the root y and square it, that's just going to be y. If I put in the 0, it's going to be nothing. So when I put in the y, it's going to be y over 2. So I could cancel that 2 with that 12, make that 6. And I'm now going to have z e to the zy squared times y. And now I want to integrate this from y with respect to y. Again, my limits were 0 and 1 for both y and z. And so how this looks, z is constant, so I'm not worried about that z. In fact, I could pull it out if I want. I'm going to do a u substitution. If I let u equal zy squared, now I'm integrating with respect to y, so it's more like a partial of u. The partial of u with respect to y would be 2zy. So then, you know how u substitution works, and of course I can move that over. So it's kind of like the partial of u is 2zy times the partial with respect to y. I already have a z and a y. What I'm missing is that 2. So I'm going to wish for a 2, compensate outside with a 1/2. And essentially, this is just going to turn into 1/2 the integral of e to the u du, which is e to the u, or in this case, it's going to be e to the zy squared. So I'm going to have e to the zy squared. We integrated this one with respect to y, so those limits would be from y equals 0 to y equals 1. And then I still have one more integration to go with respect to z. But if y is 1, I'm going to get e to the z. If y is 0, this is e to the 0, which is just 1. And we're almost there. Antiderivative of e to the z is e to the z minus z from 1 to 0 gives me e minus 1 minus e to the 0 minus 0. E to the 0 is 1. So e minus 1 minus 1 looks like my final answer is e minus 2. There you go. So if you're having trouble integrating something, remember that there is the option of switching the order of integration to an order that makes the integration easier. So you should be prepared to do that. Thanks for watching the video.